Thank you. So, first of all, thank you for the invitation and thank you all for coming as well. I'm very pleased to be able to give the opening talk here at the summer school. Before I start, I'll introduce the machine listening lab. We have a few different sort of groups within EECS and so on. So I am associated with the Centre for Intelligent Sensing, and I'm going to be talking about the audio modality for the whole of this talk. Within the Centre for Digital Music and a few other associated people, we have a grouping called the Machine Listening Lab, where we focus on essentially applying machine learning to audio. And so that's led by myself and Emmanuel Benetos, and there are various different things we work on here. So I've worked on music, I've worked on voice sounds and other things. And as we heard in the intro, I am working purely on bird sounds at the moment, or my main project is on bird sounds, and so that's what I'm going to be talking about. So my work is funded by this 5-year EPSRC fellowship, structured machine listening for soundscapes with multiple birds. So we have, the general idea is that we have large amounts of audio data, which are recordings from outdoors, uncontrolled recordings outdoors in the wild, and we want to infer as much detail as we can from that. You might be wondering why. And you might be wondering what the use of this is. I mean, these are fascinating signals in themselves. I mean, you know how interesting birdsong is. If you hear a bird, you think, like, why is it making that particular sound? Why is it the same sound as yesterday? Is it a different sound? There are lots of utilitarian questions we can ask. So here we have a spectrogram. So this is about 10 seconds of audio, and time is on the x-axis and frequency from low to high on the y-axis. Lots of different questions we can ask. Let's just hear a little bit. So this is the following sound. So there's a lot of sounds happening in parallel, starting, stopping. And very relaxing. But the questions we can ask, so which species were there in the sound signal? How many birds were there? Are they singing in response to neighbours? Is there some kind of interaction between the birds? Those kind of things are evident from the signal, and we know especially from bird behaviour experiments that the information is there because birds can pick up on it. And so the prospect is that with modern machine learning and signal processing, we can, and especially with large data sets, we can answer a lot of these questions. But again, why would we want to do this? Okay, so this graph shows how the declines in bird populations have progressed over since the 1970s. It's actually shocking when you look at the stats. A lot of bird populations have declined in numbers by around 50%. This is data for the UK. The same is true in France, in other parts of Europe, and for the USA. This is a worldwide phenomenon largely driven by farming practices and the growth of human populations, and of course climate change is a contributory factor as well. So there's a real need to monitor birds out there in the wild. All kinds of birds, birds which make interesting sounds, birds which make boring sounds, whatever. There's a need there, but there's also an opportunity. For a lot of birds, audio is by far the best medium for detecting and monitoring them. I mean, you know this from your everyday experience. And bioacoustic monitoring has now entered its big data era. So there are a lot of projects now which are placing sets of microphones in forests or on cliff edges or other places, collecting large amounts of data. So we have the need, we have the opportunity, and there are very few people actually working on applying intelligent sensing to wildlife data, but there is a need. I would encourage a lot of you to get interested in it if you can. But there's more that we can do. So before I get into the main part of the talk, I'm going to just give you a couple of postcards of the other sort of specific applications that we've developed. So this application to monitoring is very useful, and that just needs sort of high level, we want to detect birds, but we can get more detail out of it. So In a collaboration with David Clayton's lab here at Queen Mary and also with the Max Planck in Germany, we did this work where we take groups of birds, so recordings from groups of birds, and we look at how the birds are influencing each other through the calls. So when you have a group of birds together, you hear a lot of calling, but is that completely incoherent? Is it just random? Or are they actually influencing each other? And it turns out that you can detect the patterns of influence purely from the timing of the calls. So actually, the temporal structure in there, in the group, is conveying a lot of information. The second postcard, this is a nice piece of work that is based on, again, a collaboration with my collaborators in Germany. Here we have a jackdaw, and what my collaborators wanted to know is, what do they do all day? So to answer that, they put little backpack microphones onto the birds, and then they let the birds fly off. Now, you can look at bird behaviour in the lab, but there are so many differences from the bird behaviour in the wild that you really do need to study them in the wild. So there are a few groups that do this kind of thing. You can't actually put a lot of equipment on a bird's back. So you can't put a whole set of accelerometers and things like that. So in this case, we're really just looking at the microphone recordings. And the particular advantage they were looking for there was, you could put a GPS transponder on the back of a bird and you can see where they go. So you know it's a forest or it's grassland or something like that. But what you don't get from that is, what's the actual context? Is the bird interacting with other birds? Are there other species around that it might be reacting to? And what is it actually doing when it's in a particular location? So with my collaborators and also with Emmanuel Benetos, who I mentioned earlier, we took these long audio recordings, and then, so it's a little bit hard to see on this screen, but we have a list of different activities that the bird is doing up here, which include feeding, bathing, flying, things like that, and that's visible in the spectrogram there, and then we try and automatically infer from the sound only what the bird is doing. I want to give you a bit of an example of this. So I'm going to play this video. So this is just a jackdaw leaving the nest. And we'll hear the sound with an external microphone just nearby. And then we'll hear the sound from the backpack monitored bird. Okay, now the backpack. Alright, so you see what a strange sound recording it is, okay? So it's very, very close to the bird, and especially as you heard right at the end, when it's flying, you get this really powerful sound as it's flying, which is pretty straightforward to detect. But you see, so we have this slightly unusual acoustic data that we're then applying the methods that we use for other purposes, and we repurpose it to do a kind of diary of what the bird is doing all day. Oh, I'll play you this one other example. So this is a quick recording of a bird bathing in a little puddle, and just listen to the sound and see if you think you could work out what the bird is doing from the sound. See, so it's mostly just a lot of rustling sound. It's quite a difficult task, but there is information in there, and there's also information, maybe you heard there were some other birds in the background, so there's contextual information that is there in the sound recording. Yeah. So those are postcards of a couple of specific applications. In the main part of the talk, I want to talk about the following things. We're looking at the state of the art in applying machine learning to sound signals. And yes, so I do realise that a lot of you are not necessarily going to be working with bird sounds, so I hope that I've pitched this so that we can learn a lot about how we might apply machine learning to audio in general, or to other time series perhaps. So we'll get something of the general state of the art from that, as well as customising the methods for the specific application, in this case bird sounds. And recently we've looked at what might seem like peripheral issues, but machine learning that generalises well and which works well with limited data sets. These things are really important when you actually try to apply machine learning in the world. And if all of that doesn't actually satisfy you, at least there'll be some pictures of birds. So, the state of the art in applying machine learning to, well, or in intelligent sensing with machine learning and sound. Here's the spectrogram again that I showed you before, so about 10 seconds of sound. So starting from a point of no knowledge about bird sounds, how might we analyse this? You can see there's a lot of structure in there. There's low frequencies, high frequencies, there's some repetition, there are other things going on in there. And bird sound is not the first type of sound to have been studied. You're probably aware of speech recognition, you may be aware of music recognition services. So let's quickly cover a couple of those things. When I first started working on bird sounds, people said, why don't you just use Shazam, which is, at the time at least, was a popular service for detecting a piece of music. So if some music is playing in the background, you record a few seconds of it and it tells you what it is. Shazam's quite an interesting algorithm. It's an example of fingerprinting, and what they do is they take if you imagine this as being a landscape, they find the peaks in this landscape and the exact separation between these peaks. So this exact separation in time and in frequency. Those are sort of high resolution pieces of information which are very unlikely to happen by chance, assuming you collect enough of these statistics, unless that particular piece of music is playing. So it works very well as a fingerprint to look up in a database a certain piece of music. But it doesn't work for organic sounds. Maybe you have some idea why. In fact, a music recording is a very fixed signal. It's essentially the same set of peaks again and again, whereas if I say the same word again and again, the actual set of peaks isn't quite what it was before, and so this type of fingerprinting approach is not robust. That's why we don't use fingerprinting to do speech recognition, but it's also why it's not particularly useful for bird sound recognition. Onto speech recognition. For decades, the state of the art in speech recognition has been hidden Markov models. And if we apply that to our spectrogram here, what we do essentially is we're building a probabilistic model of how one frame, so one column in this picture, one moment in time, we're building a probabilistic model of how we move from one moment to the next moment. So this for speech is particularly handy if you have a recording where you know that there is one person speaking, usually one person close to the microphone. You can imagine there is some kind of causal connection there. And that's essentially the principle that's being used here. A hidden Markov model is a very general statistical technique. It's a very simple, very general model and useful. It's a bit tricky to apply this to bird sound, especially a complex sound scene like this, because actually the process that moves us from one moment to the next involves lots of separate, possibly independent or possibly dependent processes coming together to create this sound scene. And so, in fact, applying something like hidden Markov modeling to outdoor sound is really quite tricky in general because of the very loosely structured sound scene. Instead, you might want to do perhaps some sort of source separation before you're going to do hidden Markov modeling. I'm not going to cover that because I'm not working on source separation myself. And I said this was the state of the art in speech recognition. In fact, speech recognition generally now has moved on to deep learning. Perhaps you're aware of this. Deep learning has touched a lot of things, certainly including speech recognition. And in fact, deep learning is what I'm going to focus on for most of the rest of this talk. And yes, deep learning is very useful for a lot of the work we do in audio scene processing. It's very difficult to do a diagram of specifically what deep learning would do with this particular image. Let me just get a little poll before I go into this. How many of you work with deep learning practically now? Okay, so it's something of a minority. So bear with me. I'm just going to give a very simple, sort of a fairly superficial overview of deep learning here. So deep learning is, or neural networks are general function approximators. We take some input and we're going to produce an output, and so that is our function. In this example, though, the input, I've put these 4 dots at the top there. Those 4 dots represent, in this case, let's say they are individual pixels in that image that I showed you before. So that spectrogram, let's just think of it as an image for now. If we take the pixels of that image and put them through some kind of function, each one of those arrows is a multiplication, so we're transforming the data progressively. Transforming and adding and modifying the data, and then producing some kind of output. Now, the way it's trained is by putting an image in there, passing it through this set of operations, producing an estimated output, and then we train it in a supervised manner with knowledge of what we think we know the output should have been. We calculate the error and we actually backpropagate that through the network. This is called backpropagation of errors. So we propagate forwards, we find out what the error was, and we backpropagate through, and that lets us tweak each of these arrows, tweak each of the multiplications. So I'm not going to go into more detail about how the training works, but it's basically just the forward propagation and the back propagation to bear in mind. I'll come back to those in one of the later topics. That's the basics of how deep learning is trained. There's a lot more there's a lot more tricks to it, which is what makes modern deep learning work very well. There's a lot of good writing on that topic. I said that these are general function approximators. Each one of those arrows in my diagram is a separate, let's say, transformation of the data, which needs to be learnt from the data. So each one of those arrows represents more parameters in the model. It's a very over-parameterized model in general. And one of the very common modifications is to try and reduce those number of parameters. So on the left is a deep, well, it's a deep-ish neural network. We call this a densely connected neural network, because everything in each layer is connected to everything in the next layer with complete freedom. On the right, we've got a convolutional neural network. So if we imagine just taking this and applying some simplifying heuristics. One thing which we might want to do, especially in this this acoustic analysis context, if we take this data and shift it a little bit in time, then the semantics of this hasn't really changed. I mean, the semantics has just been shifted in time. So there is some kind of invariance that we want to build into there. Convolutional neural networks essentially do that. On the right-hand side, I've coloured in the arrows, and so, for example, the green arrows, we can think of them as being separate projections, or we can think of them as being, but actually the weights, the parameters are actually completely tied together. So for those 3 green arrows that you see there, they actually have the exact same weight. We're imposing a translation invariance on the structure of the network. We're also imposing a kind of locality. So I've drawn that this second neuron connects to the first, second, third items here. I've not connected it to this one over here on the far side, and so that's imposing a kind of locality assumption. So we're assuming that the effects that we want to model, or at least the function that we want to model, has some kind of locality in that things that are 10 seconds away from other things don't tend to have any usable relationship. So we've actually removed some of the weights, the parameters entirely, and tied a lot of the rest of them together. We've dramatically reduced the number of parameters. That's a large part of why convolutional neural networks are useful in a lot of situations, much easier to train. And this shift in variance and locality, usually these are useful heuristics. They're not always strictly appropriate to your situation, but in a lot of cases, such as in these audio analysis applications, they are. And so convolutional neural nets, CNNs, convnets, you'll see them everywhere. You may also hear about recurrent neural networks. Now, one thing I just want to come back to is, if a convolutional neural net has an idea of locality, so we have some repeated sounds here, let's say that a convolutional neural net is sort of implying a kind of locality where it sort of ignores, in terms of understanding this sound, it ignores things from the distant past and concentrates on a fairly local region. We might wish to do a little bit better than that and have some kind of idea of temporal memory, and that's done in recurrent neural networks. I don't directly have a diagram for that actually, but in the HMM case, you imagine that the sort of information being passed forward from one frame to the next. One way of doing that within a standard deep neural network is actually to connect, if these are individual time frames, we can actually connect arrows directly from one to the next. It's a little bit more complicated than that, but essentially we're just passing information forward in time rather than forgetting it and doing it afresh for every single moment of time that comes in. And it's pretty, so there's some good work in the past year or two which puts convolutional together with recurrent neural networks. I know you can't read the writing on here very well, but we've got a convolutional block and then a recurrent block here. And there are a few different works at the moment that take spectrogram type data for audio, put it through convolutional transformations. Here we've got 3 layers, and then here we've got 2 layers of recurrence. So the convolution does all that kind of transformation that I talked about, and the recurrence is intended to model something about the sort of temporal structure of the sound scene. So if there is a long-term memory that is needed in terms of understanding the context, then we expect that to be handled in the recurrent layers. And then finally, you boil down to the decision you're going to make. So there are a couple of papers on that do pretty well. So convolutional neural nets and convolutional and recurrent neural nets are certainly among the main things that we see performing well at the moment. So we're going to come back to some of those issues in neural networks. I'll try to refer back to some of the themes that I've talked about. Let's see it applied to birds. Bird species classification. Anyone? It's a chaffinch. So yes, anyway, it's a chaffinch, and you would recognise it by the sound as well. It's a it's a European bird, also well common in Britain. And sound is something like. It has this sort of structure to the sound in some of the different phases, and it's really noticeable. Once you learn to recognise it, it's really noticeable, and there's a lot of structure in there. It's a great example of how automatic classification should be possible. As I said at the start, if we can do monitoring by recognising which species are present, then that's really useful, but only if it's going to work out in realistic conditions out there in the wild. There have been there's actually been there's a challenge. It's called Bird Cliff, which has been running every year in automatic species classification, and the state of the art progresses really well. Actually, the results are very good, and these are across hundreds of species. So the number of classes to recognise is very large, and actually the data used to train this is really quite uncontrolled. So the data is essentially just crowdsourced recordings of birds going into this, and yet systems can do really well. So what I'm going to do is just talk through how we developed a system which got a very good score in one of these challenges, and our approach to it. So there is a paper about it. Again, we have a spectrogram here, and we think, where is the information in that spectrogram? So I should have put the previous, no, we haven't got it, okay. There's a lot of structure in a typical bird song spectrogram, and a lot of very fine detail, okay? So it's not so much taking an idea of average distribution of energy in frequency bands. That can be useful in distinguishing high-pitched birds from low-pitched birds, but it discards a lot of the detail. So what we want to do is make sure we include a lot of the fine detail in there. What I've highlighted here is a section of 4 frames of this spectrogram, and it goes the full frequency bandwidth. When people work with convolutional neural nets, they often talk about the convolutional filters. Let me just go back to the slide here. So this input where we have a green and then a red and then a purple. So the green, red, purple pattern is talked of as if it's a kind of filter that's being convolved, slid over the input data. So this green, red, purple is the filter that's being learnt. And in our case, we design it deliberately so that the filter reaches across the full spectrum bandwidth and a fairly short temporal span, but it's going to cover, despite the short temporal span, it's going to capture quite a lot of detail, even in those individual filters. What you see here is a selection of those filters that have been learnt from the data. A lot of them representing compact energy within specific frequency bands. This is learnt from large amounts of data from Brazil, and so as well as the compact energy at specific frequencies, there are single attacks, there are harmonic stacks, there are a few different characteristics in there that are being learnt. And it worked. So we were surprised that it worked well enough for us to want to give it to the members of the public. We turned it into an app. It's called Warbler. It's available for Android and iOS, and it's on sale in the UK. And how it works is pretty simple. So you open the app, you record 10 seconds of bird sound, and then it gives you predictions of what bird species it thinks are present. So it's simply taking a nice simple user experience based on the classifier, just to give them this answer to a single question about the birds. We've had lots of thousands of paying users around the UK, which is very encouraging. The recordings are submitted and collected in a database, and so we've got these recordings from around the UK, which is great. We can actually take those recordings and do further research based on them. One thing that you'll find when you deploy an app and give it to the general public is that they might do things you don't expect. So here's a tweet where someone said they tested out the Warbler app on their squeaky office photocopier. And we get a lot of this. So we get a surprising amount of bird imitations. We get random recordings that might be children or might be birds, and we can't tell the difference. It's really an interesting lesson for if you're considering deploying an app or some kind of intelligent sensing out in the wild. Just be mindful of what the public might do with it. that slightly relates to the next topic, which is, as well as this question of whether a sound being submitted to our system is a bird or not, I actually found there's a lot of people with similar questions. What you see in the picture is an autonomous recorder. People often, as I said, deploy these recorders out in the wild for days, weeks, months on end. And having done this bird classification work, I met a lot of people doing these practical projects where they actually needed to detect bird sounds, simply to say if there's a bird there or not in the recording. It's not quite the same task as classifying the birds. We don't want to know what species it is, we just want to know if it's a bird or not. Does that make it easier, or does that make it harder? If we want to detect birds, do we have to detect all possible birds, whether it's an owl or a chaffinch? It's not obvious that you can develop a generic classifier or detector for that. So what we did was we had quite a lot of data to work with, so we turned this into a public challenge. We designed this data challenge with multiple data sets from the Warbler app, from elsewhere. And so we gave the public, I don't know if you've been involved in these data challenges, but we give out these labelled development sets that people can work with, and then we have this testing set where people don't know the answers, and we get them to submit the answers, and we see which algorithm has performed the best. Now, we have this training set, so for each of these data sets we have 10-second recordings, and it's simply a binary classification. Is there any bird in this recording? This data is all from around the UK. This testing data comes from a collaborator who's recorded in the Chernobyl exclusion zone. So those come from remote monitoring systems out in the wild in Chernobyl. So one thing that you might be thinking is, why are the training sets and the testing sets so different from one another? This is quite an unusual setup. When you design a machine learning experiment, you very often try to get the training set and the testing set to match up as well as possible. I mean, you don't want the experiment to be confounded, but you do want the training set to be representative of the testing set. At least that's what a lot of people aim for. So why are we doing this? Smartphone recordings to train, remote monitoring recordings to test, UK recordings to train, Chernobyl recordings to test. This is because in practice this is what happens. The people that I collaborate with and the people that I have conversations with, they want to use intelligent sensing projects to deploy into a new area and to detect or classify birds. And if a system only works when it has training data that matches really well, firstly, that's not very useful for them. And secondly, we might question what kind of generalization properties the algorithm actually has. Can we build classifiers that actually successfully generalize? In order to do that, they don't need to, well, they need to have some kind of constraint so that they aren't focusing too narrowly on, for example, British bird sounds. And yeah, so pretty commonly, as I said, we have a training set, and then you might validate, and you also have a test set. And in a lot of papers applying machine learning, that's what you see. And then what commonly happens is biologists, bioacoustics people who I work with, they read this paper, they might download the technology or even buy the technology, and then they really test it, and then they find out that it doesn't work. So this is what we wanted to get around. We wanted to do the really test bit as part of academic, development of this field. And so I do want to encourage you to do this kind of thing. Testing in matched conditions is good, but testing in mismatched conditions is educational in other ways. So we had some great outcomes. So we had a lot of teams submitting and very strong results, actually surprisingly strong results. I was really impressed by this. This table is just the top few. So we had a few, as I said, convolutional neural nets and convolutional recurrent neural nets getting the strongest scores here. we were encouraging the use of domain adaptation, which means methods that automatically kind of reconfigure a classifier for the new conditions. I think there's at least one talk at the summer school today which is going to refer to these kind of topics. I'll be very interested to hear it. In this work, the domain adaptation didn't provide a very large boost. Yes, and so that wasn't so much an issue. But what was an issue, do we have that in the plot? No. So a lot of data augmentation and simply correctly architecturing the neural network so that it wasn't overfitting to the particular conditions seemed to be the best strategy to be used here. We have more results from the Bird Audio Detection Challenge version 2, but I'm not allowed to tell you them yet. So in about a month's time we'll be releasing the new results from this, and it's very interesting. In the final part of this talk, I want to move down onto the slightly finer scale. So bird detection, I think, is probably the best example in my domain of a challenge which is a big data situation. We take all of the audio files in the world and we divide them into two classes. Has a bird, doesn't have a bird. Okay, so we can easily treat that as a big data situation. We can train with tens of thousands of audio files. But what about tasks with much fewer available data? For example, identifying individual birds. It's very common that we might want to say, is this bird the same bird that was here yesterday? Is this the same bird that was here last year? There are very good monitoring reasons why we want to do that. But of course, with an individual bird, we only have very few recordings. There are various approaches to this, and you might think, why not just wait until you have more data? In practice, that's completely unsatisfactory. So one is the example I gave you, where there are tasks where we necessarily have very little data. We also have so many tasks in bioacoustics that people want to solve. There's not going to be enough detailed transcription to address all of these things. So in our field, we need to develop methods that will work on low resource tasks. I've already talked about individual bird ID. I'm actually just going to skip on to the second example, which is automatic wildlife transcription. So this is the work of Veronica Morphy, who's my PhD student. So the example here is going to be where we have training data, but the training data actually isn't very large and isn't actually rich enough to solve the task that we want to solve. We want to transcribe everything that's going on in a sound scene. That's essentially the sort of headline aim of my fellowship project. And so if we have spectrogram here, we have time, species. We want to know if there's a robin here, a blackbird, a robin. We want to know who is vocalizing and when. If we have that kind of information, then we can do more work. We can do behavioral analysis and so on. So it's a bit like automatic music transcription, if any of you work with that, or speaker diarization, if you work with speech technology. Actually, the biggest difference is a lot of the sounds are inherently rare. Often the sounds of interest are rare because the birds are rare. And additionally, it's very difficult to collect annotations. We can't get the birds to annotate the data ourselves, at least not efficiently. And the ornithology expertise needed to annotate these things correctly is obviously difficult to get. We can't just use simple crowdsourcing, for example. And so we're going to work in a paradigm called weakly labelled learning or weakly supervised learning. In general, although we want the thing on the right-hand side, the training data is much weaker. It contains less information. We often get recordings which simply say there is a robin, there is a blackbird, there is not a moorhen. So we have these labels which cover the whole recording but don't give us the temporal detail. And I'm talking about the training data here. So the training data isn't even good enough to directly address the task we want to address. This is in weakly labelled learning. It has been addressed in a few different ways. A simple hack is what we call false strong labelling. In the training data, we pretend that things that are never present, we know that they're never present, so we can set zeros here, that's fine. The things that are present sometimes, we pretend that they're present always. And so we can use that as training data because it is at least at the right resolution for the task we're trying to solve. We know that there's a mismatch. Okay, we know for sure that this is not quite the right training data. We might think that it might bias the learning towards too many false positives. Another approach that's been developed in weakly supervised learning is called multi-instance learning, and it's based on the simple fact that considering this transcription as a matrix, if we take the maximum over the time axis, so if we take the maximum over time, we have 1, 1, 0 in this example. If we take the maximum over what we're trying to achieve, we actually get something that corresponds to our weak labels over there. And so we can train a deep learning system using this max objective. And what happens is that, let me go on to the next slide actually. So, back to the convolutional recurrent neural network that I showed you before. So we take the input data and we propagate forward the prediction. So we're making predictions for every time instance. And then if we compare that to that's slightly wrong, never mind. And then ideally we'd like to compare that to the actual ground truth for every moment in time. But what happens is, because we don't know the ground truth for every moment in time, we simply take the max over this. You see this shaded one here is the strongest of the activations, and that's what we compare. Now, in training a neural network, we want to be able to backpropagate through this thing. It's essentially just a convenient fact that we can backpropagate through this max. So although we don't know the amount of error here, we do know that this strongest one should be 1. And so we can backpropagate the errors through there, and training proceeds. And so we show it more examples. This is just a single training example. We show it more examples, and gradually it learns to do what it should do. The limitation there is that we're only backpropagating through this. Whatever the prediction for all of the other time points was, it actually has no effect on the training, other than allowing the max to have happened here. It has no effect on the error calculation that goes into the backpropagation. So it is much more limited. That limitation means that it's going to be slower to train, perhaps less robust to train. It's a little bit of a problem. So actually, although I talked about the false strong labelling as being naive and biased, the advantage that it does have is that it actually backpropagates information through every time point, and so it might actually be a more efficient way of learning, even if it's a biased way of learning. So you still have to ask which is going to be the best way of doing it. So beyond that, the work that my student Veronica has been working on is improving on this objective function. So okay, we know what the max of these things should be. Maybe we know what the minimum of these things should be. Maybe we know what the mean of these things should be. And so if we take these different statistics over time, we can actually put them all together into the loss function, and we can calculate more statistics from our prediction and compare them against the weak label. And actually we get in the backpropagation step, we get some error being backpropagated through every one of these points, because, for example, the mean function, of course, is the sum of these divided by the count of them, and so it's so if a particular error at any point is going to backpropagate through the prediction and actually update the network. A couple of examples of how that actually works in practice. Here we've got three cases. This one's a negative one. You can see some energy in the top band there, but that's actually not bird sound. And then two positive ones where you can see those structured bits of sound coming in. And here we have the network after training for 50 epochs, training for 500. So you can see a little bit how the training progresses. This negative example is a problem because here in the false strong labeling approach, it's actually predicting positive, even though it should be predicting negative for this negative example. We've got some structure coming out here. You see there's a positive, there's a bird sound there, and there is at least an increase, a local increase in the prediction there, but actually that's getting washed out. The false strong labeling in our work seems indeed to be very biased and not ideal for these kind of conditions, especially when you have limited sizes of data sets. Let's compare that against the max objective. So that's another sort of, that's perhaps the main example from the existing literature. So with the max objective, so look at this now, this is really good. So we've got these, in this recording, 3 bird sounds, and we've got these nice 3 clear detections there. Over on the right hand side we also have, although it's a little bit harder to read, we have some pretty good detections. On this negative example, it's problematic here. We're still getting a lot of false positives there. But with the exact same amount of training, but with this, just with the slightly tweaked loss function, we can get much clearer training with this improved multi-instance objective. So for these positive examples, again you see that it's spiking at the right time. In this negative example, it's doing a lot better. So the general statistics bear this out. In this talk, I'm only just showing it you through examples, just so you can get a bit of an idea of how the training affects the sort of behavior on a case-by-case basis. We just had just last week had the journal paper out on this, so allow me to highlight that. So this is Veronica's work, published in Applied Sciences. Putting it all together. So I started by talking about large-scale tasks, bird detection and bird species classification, and essentially we take neural networks, we take a lot of the lessons from deep learning and use those. We make some modifications, we do some customizations, and we take care of issues such as generalization. And those feed into the more fine-grained analysis. So we do want to put all these things together. We want to develop a workflow where we're actually detecting birds, classifying, looking at the fine detail as part of an integrated workflow. I've talked about all these things as separate tasks at the moment. We would like to connect these things together. Now, in the more fine-grained analysis, you do need to take care to try and constrain the problem, and so that's what I talked about in this weakly labelled learning example. You can't, well, if the data itself isn't strong enough or large enough to constrain the problem for you, then you need to put part of that into the way you design the learner, in this case the neural network. I also would talk about the choice of features. I've not given myself time in this presentation to talk about the choice of features. We've simply taken the spectrogram as the input, okay? So we've assumed that the spectrum is in the main presentation. But there are still open questions about what is the best kind of data to put into a neural network. And so we put it all together. We've got large amounts of sound recordings, large amounts of bird sound recordings available at the moment, and we can recover generalities and also the fine details. The different models that we use, the different inferences that we make interact with each other, and so the bigger picture, the more long-term program is how can we do integrated solution of all these tasks. This can be through perhaps transfer learning or other methods, but taking these individual tasks and then combining them into general machine listening for natural sound is an ongoing program. So So, audio analysis. I hope I've shown you some examples which persuade you that there are a lot of interesting open problems in audio analysis. I want to say that it's, in general, audio analysis is great for as a topic for machine learning development in time series analysis. We've had a lot of work in speech recognition for decades and decades. We've also had work on music. Now we're having work on wildlife sound. You see that in each case it's productive, very productive to look at these tasks. It's not simply a case of apply the speech recognition learnings from the decade before. In particular, bird sound analysis, I would argue, is not only interesting but also particularly useful, because there are a lot of projects out there, largely governmental and non-governmental organisations, that are actually demanding this kind of intelligence for monitoring birds in the wild, understanding animal behaviour. There are challenges to overcome. We have limited data, we have unlabelled data, as I said. We can't, in general, ask the birds what's going on in these particular sound scenes, and so that's an interesting academic challenge. Okay, so I am coming from a computer science perspective. I'm not trying to understand what the birds are saying to each other, but I work with people who do. You know, maybe we can work towards this, using some of this machine learning as part of that. So I want to thank the Machine Listening Lab, which is the the main sort of context within which I work. Also the many collaborators that I've mentioned through the talk, EPSRC for funding, and I want to thank you for listening. Thank you.